Today I'll be presenting on neutron activation analysis for flux measurements in active interrogation. Active interrogation induces photonuclear reactions in special nuclear material, making their energy signatures more easily detected. The detectors we'd like to use in active interrogation are highly susceptible to pileup from the intense photon flux environment. We are investigating using an artificial neural network to classify particles more accurately than charge integration can in this environment. To do so, we're looking at neutron activation analysis as a validation method for the neural network to determine neutron flux emitted by a target such as highly enriched uranium with no photon sensitivity, avoiding all of those pileup effects. This work specifically addresses the signals and source terms for non-proliferation MTV thrust area. Active interrogation increases the accuracy of special nuclear material detection, reducing dangerous transportation of illicit materials. So through solidifying neutron activation analysis as a validation for active interrogation, we seek to combat nuclear terrorism further. In our NAA experiments, our LINAC produces a 9 MeV Bremsstrahlung photon beam directed at our target. Photonuclear reactions in our target emit neutrons into our foil, which causes activation of the nuclei of the foil. This whole irradiation process occurs from time 0 to T0 on our activity versus time graph here. At T0, irradiation stops and we move our foil from T0 to T1 from the target to our high purity germanium detector, and then from T1 to T2, the detector counts the gammas emitted as our foil nuclei decay. We have used aluminum and iron, shown down here in figure 1, as our foil materials, as the aluminum-27 and iron-56 NP reactions have some fast neutron energy thresholds at 1.9 and 3 MeV respectively. Depleted uranium is our special nuclear material target. Lead is a control target, and you can see why over here. The lead spectrum in blue has very little overlap with our aluminum reaction cross-section and absolutely no overlap with this pink iron reaction cross-section, as opposed to the black DU spectrum, which has significant overlap with both of these cross-sections. Additionally, there's a lot of lead in the collimator and it's a common shielding material, so we want to make sure that we're not seeing any activation that's not due to special nuclear material that we're looking for. So moving into some results, first for aluminum on the top here, at the 843 and 1014 keV energies that we expect, we see significant DU activation above all of the other spectra listed here. So no activation in active background shows that there's no photo activation, and no cyan lead activation shows that our neutron energy threshold is functioning as we'd like it to, filtering out all of those lower energy neutrons that we don't care as much about. Moving into iron, our blue DU activation spectra again see significant activation at the expected peaks. However, as you can see here, there is some red activation corresponding to active background at this peak right here. What we think is happening is that there's a manganese impurity in our iron sample. The manganese 55 N-gamma reaction has the same daughter isotope as this iron reaction, and additionally this reaction right here has no threshold, so photoneutrons from the lead collimator or shielding around the lab could potentially be causing this red activation right here. We could resolve this through some active background subtraction, or alternatively just obtaining a more pure sample of iron. Moving into next steps, we'd like to actually begin calculating the flux emitted by our targets using cross-section approximations integrated across the neutron spectra emitted by those targets. Additionally, for future presentations, I plan to present a little more in depth on the foil materials that we've used and other possibilities at the ANS student conference coming up, and we are currently drafting a paper for journal publication with full results. Finally, I'd like to acknowledge and thank MTV, the DOE, and DHS for funding and supporting this project. Thank you all very much.